Our next talk is from Joe. It's called Molly.jl. So as you probably all know that molecular dynamics is an extremely difficult environment. That is extremely complex dynamics and also very big, like a lot of interactions happening. And I hope that Joe will uncover how Julia enables those kind of simulations of molecular dynamics.
Thanks very much for the introduction, and thanks for braving the weather to be here today. So this talks about a package which I started development of about 6 years ago now as a way to actually learn, to be honest, learn Julia. And since then it's grown steadily, and it's been a kind of major development focus for the last 2 years or so, because I use it in my research. So what is molecular dynamics? Well, you basically set up a physical system, which means you place the atoms in space somehow on your computer. You define the rules of how the atoms interact, and then you press play, basically. And pressing play means that you do numerical integration using Newton's second law of motion, F equals ma. And this is often very computationally expensive because you have to do one step after the other. There's really not very many shortcuts. I work with biologists, and MD has had many successes in biology, and it's also had uses across materials, across chemistry. It works very well in combination with experiments. So when you kind of use experimental data to validate, and then you make predictions that experimentalists can test. And as we look towards the future, we have kind of more and more compute resources. We have all this amazing machine learning, and better protein structure prediction means that these methods are just going to continue to develop. So for example, this isn't my work, but this group simulated a protein. So there's two views of the same protein here. And you can see on the bottom the time scale, they're kind of getting up to half a millisecond of simulation. And you can see the flexibility, the dynamics of the protein, and they make, in this case, a Markov state model to look at how the different states are populated throughout the simulation. And this can obtain biological insight that you just cannot get via experiment. Another example from DE Shaw Research, so they have this amazing purpose-built hardware called Anton, which allows accelerated molecular dynamics. And you can see here the SARS-CoV-2 spike glycoprotein, which is a large protein complex where some residues are glycosylated, so they have kind of sugar groups attached, and you can see those vibrating around. And again, this kind of gives us insight into how these proteins work. So where has it been successful? Well, if you want to fold small, fast-folding proteins, you can just about do that. So this work on the right, again from DE Shaw Lab, it's quite old now, but they show that you can simulate these small proteins and they adopt the right structures. You can commonly use it for mechanistic interpretation. So, why at an atomic level is my experiment showing this? And you can kind of have this feedback loop between experimentalists and computational people. You get atomic level resolution at every single time step, which is something you just cannot get with experiment. And in the last few years, binding free energy methods, so that's where you have, for instance, a protein and a small molecule ligand, and you want to know how strongly that small molecule ligand binds, and that's become useful in pharma. However, it's not all rosy. At the critical assessment of protein structure prediction kind of competition, which is run every 2 years, MD has fairly consistently failed to predict the structure of kind of actual proteins of the size that is interesting. Disorder proteins, which don't have a fixed structure, they flop about, are too compact in many force fields. So in the bottom right here, you would want the molecular dynamics simulation to show something like the orange, and it actually shows a compact blue structure. If you want to do enzymatic reactions, you can't use classical molecular dynamics because bonds can't break, and so you have to use QMMM or pure QM simulation, which is much more expensive. And really the key concern is whether your question of interest can actually be answered on the timescale available for study. And often the truth is it just can't. So recent developments, well, Moore's law is kind of holding in the GPU space, and so the available simulation length is going up and up. Software is continuously developing to basically to make use of that GPU and kind of larger clusters, larger numbers of CPUs. Force fields have been steadily improving, as you can see on the bottom right here. This is kind of recent work in force fields to apply to all sorts of biomolecules. And I'm obviously mainly focusing on the biology case, but that applies to materials as well. Free energy perturbation methods, as I said, they're now becoming an actual part of the pharma pipeline for lead optimization, used by all the big pharma companies. And AlphaFold, which some of you may have heard of, has dramatically increased the number of proteins which are available for simulation, which is really useful as well. Probably the biggest development of the last few years has been machine learning potentials. A lot of work has shown that neural networks are able to give quantum level accuracy, but at much faster speeds, 3-4 orders of magnitude faster. Typically, these methods are trained to match forces and energies on high accuracy quantum data sets. And they do often show issues on larger simulations when you go out of domain. The field is addressing these problems along with things like long range interactions and the performance, which it's probably always going to be worse than classical force fields, but it's getting faster and faster. So these are really promising. They're not immediately applicable to larger biological systems, but there has been some work, for instance, shown on the right here, where that has been done. So what software is available for molecular simulation? Well, there's a number of excellent, really, really mature packages. I've shown some on the right here. And these really are jewels in the crown of academic software. These have, Gromacs, for instance, has been in development for many decades now. Arguably the largest and most used piece of academic code. Heavily optimized. They write routines for low-level routines for different architectures. I think at some point they thought the square root function was too slow, so they wrote their own square root function. They're really, really focused on performance. And most of these packages work the same way. They have one or more kind of fast kernels that run the simulation, whether that be in C or CUDA. And then they have some layer on top which you can interact with. So for instance, in the case of Gromacs, it would be a binary, or OpenMM would be a Python interface. And that means that most packages are hard to interact with all the way down, because at some point you run into this kind of two-language barrier, if you like. And no mature MD package has support for differentiable simulation, which I'll describe later, but basically means taking gradients through the simulation itself. So what is Molly? It's a pure Julia implementation of molecular dynamics. One language all the way down. A simulation script is just a Julia script. In terms of design, it's closest to OpenMM, which has, as I said, a Python API, and then but has multiple kind of compute kernels under the hood. The key kind of defining concept of the package is that if you define a potential as a user or a simulator or a logger, it should be easy and it should be just as fast as the built-in features. And that really matches the Julia language itself, where the standard library is largely implemented in Julia because it's fast enough. Everything is defined imperatively. It's just code. There's no kind of config files or anything. And currently, in terms of kind of correctness, it can simulate proteins with the trajectories matching OpenMM. And it's differentiable using a combination of zygote and enzyme. And the gradients match numerical gradients. So just a quick rundown of the features available. You have the fairly standard non-bonded interactions, Lennard-Jones, Coulomb, gravity, etc. You have the bonded interactions, so harmonic bonds and angles. You can read in kind of OpenMM and Gromacs force fields, and any coordinate files supported by chem files. Yesterday you heard about the amazing atoms-based interface and the atoms calculators from Rachel and Michael. And so you can, the systems in Molly implement the atoms-based interface. You can use atoms calculators in Molly, and you can also use Molly as an atoms calculator. Flexible simulators like Valet and Langevin, steepest descent minimization and thermostats. Also, we have one barostat at the minute, the Monte Carlo barostat, and variants of that. You can simulate in a triclinic box. You kind of have flexible loggers that allow you to track arbitrary properties throughout the whole simulation. We have various neighborlist implementations, including cell list map. At this JuliaCon, I heard about 2 new neighbor lists. One is spatial hash tables, and the other is point neighbors. And so I'm hoping to kind of hopefully add these as well to Molly. Implicit solvent methods. So we use unitful. It's optional whether the user uses unitful or uses no units at all. You have to choose one or the other. You can't mix them. We recommend you use unitful because it catches all sorts of errors. If you don't use units, that's fine, but you have to make sure you have in your head a kind of consistent unit system. We have some analysis, and we have kind of basic visualization, and you can run CPU threaded or on the GPU. So what's missing? Well, we have partial support for bonds and angles that are constrained in the integrator. That works on CPU in some contexts. We're missing particle mesh U automation, which is one of the long-range electrostatic methods, which are used pretty much universally for biomolecules. We don't have full virial calculation yet, which prevents some barostat implementations. The system preparation is currently fairly rigid. It's not super flexible. You can't do things like add solvents or hydrate your proteins. We don't yet have alchemical free energy calculations. The API is changing as we're trying to find the right approach. And as I mentioned, kind of due to the maturity, we have limited test coverage, and the performance is, well, I'll talk about that later, but it's still getting there. So to summarize the kind of pros and cons, it's easy to add new features. It's one language all the way down, so hopefully it's easy to understand. And the differentiable simulations are, which I'll come on to, are fast. In terms of disadvantages, it kind of lacks maturity testing and features of the really well-established software. And the GPU multi-threaded performance is somewhat below that of existing software. So let's dive in with some code. You can load in the package, and then you set up the boundary. So this is the box that you're running the simulation in. We set up some atoms using the atom type. You can use any atom type you want, for instance, your own types. We then place the coordinates randomly without clashing. We give the particles some velocity. Whoa, Jesus. Okay. Should I wait a sec or should I carry on? I'm going to wait a sec. Should we try and put it back? Or? Okay. Okay. No, that's fine. Yeah, sounds good. All right, looks like the stage didn't like molecular simulation, but nonetheless we can carry on. So we use a Leonard-Jones interaction, which is attractive at long range and repulsive at short range. We use a velocity Verlet simulator, and then we kind of set up the system using this system call. So this is something which you'll see throughout, is this idea of setting up a system and then calling simulate on it. And then we use the inbuilt visualize function, and we see that this is a kind of very, very high density simulation of some kind of gas atoms flying around. You can also set up, like in OpenMM, which is where you read from a PDB file and from a force field file. So we read in the force field, kind of past an XML file. We can also read in Gromacs files. And then we set up the system using a PDB file. In this case, we're also using loggers. So loggers track properties throughout the simulation. So we want to track the total energy. And also the conformation, which we write to a PDB file. In this case, we do a minimization. And then we apply velocities. We use a Langevin simulator, which keeps the temperature constant. And then when you simulate, you get the thing on the right. This is visualized in PyMol, but the simulation is from what you see on the left. It's not just atoms. I mentioned it's flexible. So in this case, we can simulate planets. So we take the positions and masses of the closest planets to the sun from AstroPy, and then we use a gravitational interaction We set up a system in exactly the same way. We use a Verlades grater, and in this case, you can see that indeed, if you simulate for 1 year, you indeed get what you would expect, the orbit of the planets around the sun. So this is using kind of the same abstractions as for atoms. There's 3 types of interactions between between atoms in Molly. So the first is the pairwise interaction, which is between all or most kind of pairs of atoms. So for instance, I mentioned the Leonard-Jones potential, or its kind of generalization, the Mie potential on the right. You can have specific interactions, which are between specific sets of atoms due to the topology, for instance. And then there's also a very flexible type of interaction, which is the general interaction, where you take all coordinates in and you give all the forces back, or the energy back. And that's useful for machine learning potentials, where you would just pass off the call to another library, or to density functional theory. You can, for instance, call DFTK. And so if we wanted to find a new pairwise interactions, I said it should be just as fast and easy as the built-in interactions. So there's an example on the right. You define your struct, and you can have any properties you want of the interaction there. You say that in this case that it wants to use the neighbor list, which is the list of close pairs. And then you define the force function, which takes in various arguments, and you basically can write whatever you want in there. It just has to output a static vector, which is the force. And you can also define a very similar function which outputs the energy. And that works on GPU and CPU just the same, without modification. And we're planning to allow more properties to go into that function. We've had a couple of requests for velocity-dependent forces, and also we should allow time-dependent forces. So I mentioned GPU acceleration. We use the CUDA.jl kernel language. Currently, the force summation kernel is really simple. You can basically see the whole kernel on the right here. Each thread just calculates the force for one neighboring pair, and then atomically adds it to the force array. Given how simple this is, performance is actually okay. In some cases, it's about 5 times slower than OpenMM. In other cases, it's a bit slower than that. As I'll come on to later, we're looking to develop this, but the nice thing about this is that this is all internal to Molly, so the user never sees this. The actual force functions they define are the same on CPU and GPU. An enzyme is currently the only way I know of to differentiate CUDA kernels like this, and works really nicely. So in terms of performance, if we take, for instance, a bulk water system of about 3,000 atoms, which you can see on the right, on a single thread, you get about 18 milliseconds per step, which is just over 2 times slower than OpenMM. OpenMM is probably representative of the state of the art here. Multi-threaded, we're about 4 times slower. And on GPU on this system, we're doing quite well. I'd say we're about 4 times slower, with clear room for improvement. However, on a larger protein system, we are a bit more like 20 times slower, because they can they can saturate the GPU more. I should mention as a kind of caveat, this is on a current development branch, and we use reaction field electrostatics here. So if you use units, it really doesn't slow things down much. It's actually unclear whether it slows things down at all, but if it does, maybe it's like 5–10%. So what's the route to kind of high performance? Well, on CPU, we need better use of SIMD. I've done some work on this, but I found it challenging to get this working whilst still allowing generic interactions and generic atom types. So if there are any kind of CPU whiz kids in the audience who want to help with this, do chat to me. There's a lot of room here for improvement. On GPU, we should basically do what the existing software does and use the kind of clever neighbor ordering and reductions in more complex kernels, and hopefully we should have that by the end of the year. Realistically, we're not going to reach the speed of mature specialist software on, for instance, protein simulation. However, what we can aim to be is the fastest for kind of small to medium systems with custom interactions, which are often difficult in current software. And if we want to scale to larger systems, we need to do domain decomposition, which is where you split the system up into kind of smaller cubes. And that may be a long-term goal, but it's not currently being worked on. So I mentioned differentiable simulation. It's probably easiest to introduce this with analogy to recurrent neural networks for those who are familiar with that. So if you imagine you have a sentence, a series of words, and you want to predict whether it's positive or negative, happy or sad sentence, You can use an RNN, which kind of goes through word by word, and your network updates some hidden state. And then at the end, you have the output, which is your prediction. You compare to your labeled output, which is and then you calculate some loss function, which is just a number. And because you've been clever and you've implemented this in an automatic differentiation framework, you can use backpropagation to change to get the gradients of that loss with respect to the neural network parameters. And this is how basically all neural networks are trained. And the idea of a differentiable simulation is you do the same thing, except you have your starting coordinates, you then step through the trajectory using molecular dynamics and your force field parameters. You then have some loss function. So in this case, I'm just showing what you might compare the final coordinates of your simulation to a known structure and calculate the root mean squared deviation. And then you just do the same thing. You use automatic differentiation to obtain the gradient of that loss with respect to the parameters, and that lets you improve your force field to match arbitrary properties. So for instance, in this work I did a few years ago, we started off with kind of flat zero potentials, and eventually we learned a coarse grain potential for proteins that matched what you see in the PDB. And the reason this is appealing is because you have this huge variety of possible loss functions. I mentioned earlier that when you train machine learning potentials, you just train them on quantum mechanical data, forces and energies. But here you can train on pretty much anything you can obtain from the structure. So for instance, the radius of duration, how compact things are, flexibility, whether certain regions of the protein move, how strong the binding is, and fit to experimental data, for instance, cryo-electron microscopy data. So what software is available for this? Well, there are actually packages now that have come out in the last few years. JaxMD, TorchMD, DMFF. These are all great, but they're all limited in some way, either by their scope, so they don't have biomolecular support, or by performance. They're nowhere near the speed of OpenMM and Gromacs. And so Molly can do this. It can do differentiable simulation, including on proteins, and it can do it fairly quickly. The way we do it is we use zygotes on the outside, if you like, to link everything together. And then the slower bits we call into enzymes. So we have this big file of chain rules which just call into enzyme, and including for the GPU kernels. And so my work over the last couple of years has been to apply this to improve a protein force field. So implicit solvent force fields basically replace the solvent molecules with a continuous medium for speed. So you can get rid of all your water and just look at your solute. However, they tend to overcompact disorder proteins. And so we use Molly to modify an existing force field and implicit solvent method to improve its performance on disorder proteins. And so on the right here, you can see in orange and green is the correlation of radius of duration, which is how compact these proteins are between experiment and simulation. And in the existing implicit solvent methods, which are orange and green, you see that it's a poor match. And the match of our new method in blue is much closer to the experimental values and to kind of explicit solvent simulations in purple. And if you want to read more about that, you can read about that in this paper. So we have more ongoing work. I mentioned we use zygote and enzyme. That's a problem basically because zygote doesn't allow you to do mutation, and that puts a limit on performance. So we're basically rewriting it all to use enzyme throughout, and that will allow us to kind of access the higher speeds I was mentioning before. There are a couple of blockers there. We are waiting on GPU support for broadcasting an enzyme, but I think that should be coming in fairly soon. James Sloss is adding kind of generic backend support with kernel abstractions, which we should be able to do without a loss in performance, and means that you should be able to run this on all sorts of GPUs. There is work being done on particle mesh U automation and GPU bonded angle constraints. The API may change a little bit more as we try and find the right balance. But if you have any kind of suggestions or comments, do let me know and we can work that in. And at some point there'll be a software contributor with a software paper with kind of all the contributors. So just to kind of grab bag to finish off, I've said it can do protein simulation. You can simulate bonds, so here a diatomic gas. I showed you that you can simulate arbitrary systems that aren't atoms. I didn't talk about this case much, but in this case we're just training a simple machine learning potential to reproduce a familiar logo. You can make and break bonds throughout simulations, which is quite a nice feature you can't do in existing packages. And you can also use it to just kind of explore potentials and plot them. I started my group recently at the Laboratory of Molecular Biology in Cambridge, and there's funding for postdoc positions. There's also going to be a PhD advert coming out towards the end of the year. So do chat to me if interested. And I'll just say thank you to the contributors, many of whom have been contributing for a long time now, to all the amazing Julia contributors and package authors, particularly for Zygot and Enzyme. So big thanks to Billy Moses and Valentin for basically fixing all these enzyme bugs. I think I've raised about more than 50 bugs on Enzyme, and I think more than 40 of them have been fixed, which is fantastic. Thanks to OpenMM and Gromacs for the inspiration, and the Georges and David Jones Group for support at the LMB. And finally, thank you for your attention.
Thanks. It was a great talk. Do we have questions? No? Yes. Catch the box.
Yes. Oh, thank you very much for your great talk. A growing field in biophysics is that of active matter. So in active matter simulations, you do a simulation just like this one, but then for every particle there's another stochastic process that determines the active force. This, for reasons you've mentioned, is very difficult to implement in LAMMPS or Gromacs or Blue or whatever software you like. So is this something that would be easier to do with Molly?
Oh, sorry. Excuus.
Yeah, okay, thanks. We have this general interaction type which allows all coordinates in and all forces out. So you'd probably want to write some general interaction that basically applies that stochastic force on each atom every time step. And then if you wanted to apply other forces between atoms, those would be either pairwise interactions. So it's possible. You may need to do a bit of kind of looping yourself. So you may need to loop over the atoms in that case. But I think it should be possible. Yeah, if you give it a go and it's not possible, then do let me know, because I know different fields use interactions in different ways, and my focus is very much on biomolecules, but it should be applicable to anything really.
Okay, thanks.
More question?
Okay, is there some related work on Poisson-Boltzmann simulation and molecular surface generation?
I'm not so familiar with that, so I don't think you'd be able to do that in Molly as it stands. But
Yeah, but it would be some package which would use the Molly data
I see.
and in some kind of consistent way to also allow the differentiation throughput,
yeah,
something like that.
that would be great. Yeah, and if we get something working with another package, it'd be great to have it as an example in the Molly docs to show that integration. Yeah.
Hey, Joe, great talk. You mentioned that you didn't have full virial support, or
Sorry, could you say that again?
you said that you didn't have full virial support.
Yes, that's right.
And I don't know if you still support MPT simulations at all, or
So we have virial support for pairwise interactions. However, I believe in bonded systems, the bonds and even the constraints also contribute to the virial. So we don't have full support in that sense. We don't have any piston-based barostats, but it wouldn't be too hard to implement one. The problem is it would only work on kind of gas systems, unless you were willing to compromise on the virial.
because I know that OpenMM does without virial calculations.
So OpenMM has the Monte Carlo barostat, which we have.
Okay.
So we have the Monte Carlo barostat.
Let me give you that here. Sorry?
Great, thank you.
Very much.
I also have a small question.
Yep.
So you mentioned that the Molly supports GPUs.
Yeah.
But does it also integrate well with HPC systems, high-performance computers, clusters with thousands of cores?
So at the minute, not really. There's multi-threaded CPU support. So at the minute, you'd have to have for instance, if you had a node with 256 cores, that would work. It would just use all of them. We don't have support for things like MPI or kind of multi-node or anything like that. That will probably come out as part of the domain decomposition stuff, because you generally want to, so on the right here, you generally want to split up things onto different, so that's more a long-term goal, and there's not really much point in doing that unless the performance gets kind of really competitive, but that would be a long-term goal, yeah.
Great. Extra round of applause. It was a really nice talk.
Thank you.